Hi and Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Aiman bin Fatul Zaman. My student ID is 2022614228. My group number and class are Group 20, A4AS120120, while my lecturer's name for CHM131 General Chemistry subject is Madam Nur Sakina Zorina binti Zulkifli. In this video, I'm going to talk about the first chapter that you will learn um, when study CHM131 General Chemistry, which is atoms, molecules, ions, and chemical equation. To be more specific, I'm going to talk about one of the topics of the chapter, which is topic 1.4, mole concepts, and Avogadro's number. So let us start with subtopic 1.4.1, atomic mass. So what is the definition of atomic mass? What does it mean by atomic mass? Well, the simplest term is atomic mass is it is the mass of a single atom. So, but how do we know the mass of a single atom? Which indicates the terms of atomic mass. Well, if you want to know, if you ever learn about mass numbers, or in high school we call it the nuclear number, which is the total number of protons and neutrons in a single atom. Yeah, those two particles make up the number of atomic mass. Those two are also the definitions of atomic mass. It is supposed to be electron supposed to be in it also, but due to electron having a smaller mass than those two particles, so small, sometimes the mass of the electrons can be ignored. So the terms of mass number and uh, or nuclear number just focus on two particles, protons and neutrons. So, so we know what atomic mass is, but do you know about atomic mass units? Well, atomic mass units is kind of like, I give you an example. Let's just say this is 1 meter. So the number one is the value or magnitude of the distance, but the symbol of meter, the meter or the symbol of it, which is m, is the unit of the distance. Now take that situation and apply it to atomic mass units that we are talking right now. So if we total up the number of protons and neutrons, that would form, that would be the value of the atomic mass. But the unit, same as meter, but in these terms, we use AMU, atomic mass units. Sometimes they put the letter U or Dalton, DA. It is important to know that the AMU not only expresses for atomic masses, but AMU also expresses for molecular mass. So I didn't mention the carbon 12 in the previous slide, but in case if you have watched the points there, it is mentioned about carbon 12. So, but why was the carbon 12 is selected as a reference element for calculating atomic mass? You need to understand that atoms, molecules, and ions are really, really hard to measure in grams. So much so because they have due to incredible small size. Due and because of incredible small size, of course, they would have incredible small size or okay, it's not size, it's a mass. Especially if you want to measure them in grams. So what scientists do is they compare with another atom which is chosen as the standard atom. Okay, so why was carbon? What's have to do with standard atom with carbon 12? Well, that will be explained in the next subtopic. But for this sake, it is because carbon 12 often exists in abundance and it naturally occurs. Meaning it naturally occurs, it is not synthetic, it's not created by humans, it is nature's doing it. And carbon 12, the meaning of carbon 12 often exists in abundance is all around the world. You can find it easily by maybe just at the backyard of your house, there could be carbon 12. It is so much. Um, yeah, that's the point. That's what it means by carbon 12 often exists in abundance. There's a lot in this world. In this world, there's a lot of carbon 12. So you might be thinking, well, if you want to find an atomic mass, we should just total up the number of protons and neutrons. That's it. That's how we get the atomic mass. Well, true, but that That method is one of the three methods that you can find atomic mass. The first method is you can use the periodic table to search for atomic mass. Now, when you look at the periodic table, you will see there are boxes that contains element in it. In order for you to find the atomic mass, look at the decimal. Usually they were expressed in decimal places. Yeah, usually they were expressed in decimal places. Those decimal places mostly are atomic mass. Another way to understand is if you look at each box, there is a number below the atomic symbol or the element name. Under these two is the atomic mass. As you can see the picture right here that I showed you, beneath this atomic symbol MO, there is an atomic mass of 95.94. This is an average mass. So you can use this diagram, understand it, you can find where the atomic mass in the periodic table. So the first method is you look at the periodic table to know the atomic mass. Now we look at the second method, and this is what I mentioned in the first, first three slides, is add up the protons and neutrons in one atom. Add the masses of the protons and neutrons together to determine the atomic mass of a single atom of an element. So this is this is the method that I'm talking about in the first three slides. Here is the example I have searched on the internet. You can pause this video, and that way you can understand more about how mass numbers by adding this number of protons and neutrons determine the value of the atomic mass. Here's the example. You can pause the video. Now we move to the final and the third method on how to find the atomic mass. It's by weighted average for all atoms of an element. Although an element has multiple isotopes, if you don't know what isotopes is, it is an element that has lots of atoms with similar atomic numbers or the number of protons, but a different neutron numbers. Hence, but when adding these neutron numbers, these different magnitudes of neutron numbers, and the atomic numbers, which is the number of protons, would make the different mass numbers. That is what we call an isotope. So, although an element has multiple isotopes, we can still calculate the atomic mass of an element by using the formula of relative atomic mass. Now, the meaning of relative atomic mass is average. It's the average mass of all isotopes of an element. We average it into one unified value. Okay, people tend to use this relative. Lots of elements in the periodic table use relative atomic mass because an element has a lot of isotopes. Okay, it's hard for you to find element that doesn't have any isotopes, and it shows the real atomic mass. Okay, keep in mind that relative atomic mass is not the real number of the element; it's just the average number of the element. So here's the formula. Yep. You have learned this in during high school, especially for those people who took science stream, who learn chemistry. You will be familiar with this formula. This is the formula of finding the relative atomic mass. This is what I mean the third method to find the atomic mass. You can pause this video and you can for those people who never seen this. Yes, you can pause. Never seen this equation or formula before. You can pause this video to understand it. All right. This is the example of calculation of the third method of using the relative atomic mass to determine the value of atomic mass. Here's the example. You can pause this video. Now let's move on to the next subtopic, 1.4.2, relative atomic mass. So yeah, this is what I'm talking about when the third method, finding the relative atomic mass. Yeah, this is a subtopic, and we're going to go in depth with the relative atomic mass. So buckle up. So before we go in depth about this relative atomic mass, here's a little introduction for you. So we all know that atoms, molecules, ions, and or any other particles that we know is incredibly small, and because they are incredibly small, they have incredibly small size, and because they have incredibly small size, they have incredibly small mass number, hence making it impossible or difficult to measure them, especially if you want to measure them in grams. For example, right here that I give that is presented right now is the mass of one hydrogen atom is equivalent to 0.0000000, etc., until it ends with 0.002 grams. It's how insanely the number of mass when we want to measure them in grams, our unit, our familiar unit. So because we cannot measure them in grams or it's just so difficult, scientists suggest that the mass of the different atoms, usually between two atoms, can be compared even though they cannot be weighed. Okay? We cannot measure them in grams or it's just too difficult, but we can compare. So the next question is we can compare between one atom with another atom who has chosen to be the standard atom. This is the birth of the terms of relative atomic mass, or RAM for short. So, but the RAM doesn't have any units because, like you said, due to RAM was determined through comparison between atoms and not by weighing them. Remember, we don't measure them in grams using any weighing instruments. Then it doesn't have any unit because we only compare to the standard atom. One atom compared to the standard atom. We do not weigh them. So if we want to compare them, we have to have our first standard. We need to have a standard atom, which this atom we can use this atom to compare with other atoms, so we can know their own, their own atomic mass. Okay, we cannot measure them. So the first standard atom use is the hydrogen atom because it's the lightest out of all elements discovered. Scientists set its mass precisely to 1 unit. Other elements atoms were compared with this atom at one point. So here is the diagram of how um, how this comparison of relative atomic mass works and by using the atom hydrogen as the standard atom. So here's the diagram that I have searched on the internet. You can pause this video and understand it. But the hydrogen atom was not like at the peak. Okay? It has a rock bottom. And that rock bottom, it has that the hydrogen atom has been replaced by the carbon 12. Remember? Carbon 12. Now we are going to go in depth why carbon 12 is chosen as the reference of element of comparison. Why other atoms compare with this carbon 12 to determine the atomic mass. So due to multiple errors and problems when using the hydrogen atom to determine the atom's RAM, relative atomic mass, they decided to abandon it and search for a new standard atom to compare with other atoms. In 1961, the international treaty chose an isotope of carbon, which is carbon-12, as the new standard atom due to its easily accessible in solid form at room temperatures. See that? Easily accessible, meaning it exists in abundance. The abundance of carbon-12 is almost 98.99, nearly 100%, which is that is abundance, totally abundance. While the carbon-13 and carbon-14 isotopes only comprise 1.11. Okay, so the average value of this three isotope is the equal amount of one atom of carbon-12. So this is a picture of carbon-12 as the new standard atom, replacing the hydrogen atom. So this is the picture right here. You can pause this video to understand it. Now that we know how the scientists have found the terms of relative atomic mass, let's look at the definition. So the relative atomic mass of an element is the average mass of the different isotopes of the element, right? Remember, an element always have isotopes due to difference of the numbers of neutrons, okay? That's why you have carbon 12, carbon 13, and carbon 14. Those are isotopes under the element of carbon. See, if we want to know the atomic mass, we have to use the method of relative atomic mass because it says here average mass of the different isotopes of the element. The relative atomic of an element is also defined as the average mass one atom and element compared to 1/12 times the mass of one carbon 12 atom. So this is the formula. I think I have showed you in the previous slides, but just in case I put it again, the formula for relative atomic mass. You can pause this video to understand it. So here is the calculation that I got from the internet. You can pause this video to understand how things work, how to understand how To understand how really you want to know the atomic mass by doing the third method, which is the relative atomic mass. Now we move on for the third subtopic, which is 1.4.3 mole. Okay, so what is a mole? Okay, what's the magnitude? Okay, where did it get where did it get its name from? Well, it's okay. We go one by one. Okay, so the definition of a mole with the symbol mole as a SI unit for a quantity or the quantity of a substance. You need to remember that mole MOLE and mole MOL are two different things. One MOLE is the term of the quantity of the substance. They summarize it to be the quantity of a substance. They summarize to be mole. But for MOL, mole, it is the SI unit. It is a unit of measurement, the quantity of a substance. So 1 mole of a substance contains 6.022140026 times 10 to the power of 23 basic entities of the substance. The entities could exist as atoms, molecules, an ion pair, or a subatomic particle such as an electron. So another definition for mole is the quantity of substance that contains the number of particles equal to 12 grams of carbon-12. The points below it explain it. So 12 grams of carbon-12 equals to 1 mole of carbon-12 atoms equals to 6.02 times 10 to the power of 23 carbon-12 atoms. The example is 10 moles of water, a chemical compound, and 10 moles of mercury, a chemical element. Both contain equal amounts of substance, and the mercury contains exactly one atom for each molecule of the water, despite the two having different volumes and different masses. Okay, let me explain in simple terms. So any substance, it could be water, it could be gas, it could be a block of ice or block of wood. 1 mole of the substance will always equals to 6.02 times 10 to the power of 23 particles, which in this term, it will be called as molecules, ions, and atoms. Okay, you need to just remember that. Okay, 1 mole equals 1 mole of any substance that you can find, you can see, always equals to 6.02 times 10 to the power of 23. Okay, in the previous slides, I did mention that the particles or basic entities could exist in many ways, but uh, 18 years of learning, I'm pretty sure most people will only remember three, which is atoms, molecules, and ions. So here are the examples that you can understand, which is what, for the first example, 1 mole of ferrum atoms contains 6.02 times 10 to the power 23 of ferrum atoms. Okay, 1 mole of molecule oxygen contains 6.02 times 10 to the power 23 of oxygen molecules. Okay, 1 mole of copper 2 ion contains 6.02 times to the power of 23 of copper 2 ions. Okay, so if we go back, the meaning of element is that um, inside the element, the atoms, right? Everything comes from atoms, but it must be a specific atom. So if that atom is like quote unquote ferrum, okay, the element will be ferrum, okay, ferrum. Okay, if you have a block, if you have a block of iron, another term for ferrum, okay, inside the block of iron contains only ferrum atoms. Same goes to the oxygen and also for the copper. Oxygen have two Dewey atoms. I remember it's Dewey atoms, two oxygen in covalent, they're combined in a covalent bond. Yeah. With that, in water, there will be only water, only two oxygens combined with a covalent bond. That's all. Okay. An element only contains that one specific atom. So we now know what mole is, the magnitude of moles, and what are the particles could be. Okay, it could be an atom, molecule, or ion. But did you know that mole plays a crucial role in modern chemistry, right? So the first importance is The usage of the mole term is a suitable method to express amounts of reactants and products of chemical reactions. Okay. In other words, if you want to write a formula, chemical formula, you could in the chemical equation, there's going to be a digit, right? Digit in front of the formula of the compound. So let's just say H2O, but in a chemical equation, you have two H2O. The number two in front of the H2O is the number of moles, okay? The number of moles. And moles also helps us to determine the empirical formula of uh, of a compound. Okay, so there are two molecular formula and empirical formula. In order for us to know to determine the empirical formula, we need moles. So moles help us to determine the empirical formula of the compound of any compound. Um, the mole also allows scientists to link between the subatomic world and our macroscopic worlds, units and amounts. So we know what the magnitude of mole is. Okay, it is a large number of 6.02 times 10 to the power of 23. It was a huge number, but then they simplified that number into the terms of mole. Okay, in terms of mole. Plus, um, this another explanation is the below it. Defining the mole in this way allows us to exchange between grams to moles or moles to particles, even though you can see them with your naked eye. This is what I meant. So the second point and third point parallels, okay, nearly parallels. You need moles, okay. So we now know the value of moles. So we're going to use this mole to determine grams, to determine the mass of a substance, and also the number of particles. We can now determine the number of particles in one mole, or in other words, in of a gram. Like if you have 5 grams and you want to know how many atoms, molecules, or ions exist in that 5 grams of a substance, mole helps us solve it. Now we move on. We move. Let's move away from the moles. Okay, we have explained enough about moles. Now let's look at Avogadro's constant, Na. So what is Avogadro's constant? Avogadro's constant or Avogadro's number is defined as the number of particles in one mole of a substance. Okay, the value of the constant is 6.02 times 10 to the power 23 particles. See, the number of the constant is similar to the number of one mole. Okay, so one mole is equal to Avogadro's number, 6.02 times 10 to the power 23 particles. Like I said, particles could be anything. The constant was named after a famous Italian scientist, Amedeo Avogadro, who lived from 1776 to and died at year of 1856. Okay, quick history here. I want to tell you how the Avogadro's number came to be what we know as today. So it bears the name of the Italian physicist Amedeo Avogadro, who discovered that two gases of equal volume have the same number of molecules when they are at the same temperature and pressure. The number of units a mole was referred to as Avogadro's number in the early 20th century by a French physicist, Jean Perrin. Now, you might be wondering, well, if we know the history of Avogadro's number, what is the history of the mole? Where did the term mole came from? Well, according to a few research that I did, Wilhelm Oswald was the first person to introduce the term mole. Wilhelm Oswald, who is the he is the first to introduce the term mole, MOLE, unit into chemistry around 1900s. The word mole was introduced by him also. Yeah, that's how we know the word mole. Mole is taken from a German word molecule with a K, not a C, with a K, molecule. He originally defined this unit in terms of grams. Several years later, he did make it clear that the concept of the mole should be linked to the ideal gas. Okay? Remember what I said in previous slides, that the value of the constant, Avogadro's constant, is 6.02 times 10 to the power of 23. But I did mention it was similar to the number of one mole. Yeah? Or we can indicate that the relationship between one mole and Avogadro's number and A is below. One mole equals to 1 and Avogadro's constant equals to 6.02 times 10 to the power of 23. So here is the relationship between the number of moles and particles that I have found on the internet. You can pause this video and you can try to understand it. Okay, that is the formula. So now we move to the calculation. So here is the calculation I have found on the internet also. How many moles of magnesium in 3.01 times 10 to the power 33 atoms of magnesium? Okay, as we see in the previous slides, I have showed you how we can determine the number of moles by just giving atoms. I have shown in a previous slide. So it says here 3.01 times 10 to the power 22 atoms. You have to multiply it with 1 mole over 6.02 times 10 to the power of 23 atoms. We get 5 times 10 to the power of negative 2 moles. So that's how you calculate it actually. But this is only one example, okay? You can search you can find many examples available on the internet. You can understand that, okay? This is only one example that I'm showing you. Now let's move on to the fourth subtopic, 1.4.4 molar mass. Now that we are in the topic of molar mass, let's start with the definition. What is molar mass? What is the definition of molar mass? Well, molar mass, for what is also known as molecular weight, is the mass of one mole of a substance. Yeah, even one mole has a mass, and that mass is called molar mass. Okay, the standard unit for the molar mass is G mole negative 1. So at the right of the screen, it explains how molar mass works. So the molar mass of a substance equals to mass of one mole of a substance. Yep, remember the definition. So the molar mass of a substance is equals also to mass of 6.02 times 10 to the power 23 particles, because one mole equals to 6.02 times 10 to the power 23. So since the molar mass is the mass of one mole, so the molar mass of a substance is the mass of 6.02 times 10 to the power of 23 particles. So here's how you can find the molar mass of carbon-12. Okay, we're going to use the example of carbon-12. So the molar mass of carbon-12 is 12 G mole negative 1. The relative atomic mass of carbon-12 is 12. Therefore, the molar mass of carbon-12 equals to the relative atomic mass of carbon-12, meaning that, mm, if you want to know what the molar mass of an element is, just go to the periodic table and look. Like I said, the usually in decimal places, the value decimal places at the bottom of the box of each element. Okay, that is called an atomic mass. So like I said, relative is the average. It is still under the terms of atomic mass. It's just this. It is an average mass of the element. Okay. So the molar mass of carbon-12 is equal to the relative atomic mass of carbon-12. Technically, you could say the molar mass of carbon-12 is technically equals to atomic mass of carbon-12. There's no really official, there's no difference or any reason as to why it happens this way. But according to my research, this is how it operates. Well, in the previous slide, and the slide before, we used the example of carbon-12 on how to find the molar mass. But it isn't reserved for carbon-12 only. Any elements, like it said here, in similar situations, the molar mass of other substance will always equal to their respective relative mass numbers. It could be atomic mass or formula mass or molecular mass. Any relative mass that the compound or an element has. It will be always equals to the molar mass. So if you find the relative mass of an element or a compound, you will find the molar mass of the substance. So here's the picture that I got from the internet. Yep, you can find their respective relative atomic mass on the periodic table to find the molar mass. As you can see there, the relative atomic mass, it shows, the picture shows, the diagram shows the relative atomic mass. Where is it located in each of the box in the periodic table? So you can pause this video to understand it. So here is the example of calculations that I have found on the internet on how to find the molar mass by looking up the relative atomic mass that you can see, that you can find on the periodic table. I'm so sorry, I cannot say periodic table fast, so I'm just gonna say it slowly. Yeah, never mind. Ignore that. You can pause this video to understand it. Now, okay, when we talk about molar mass here, it is still under the concept of moles, okay? It links with the mole. So when it links to the mole, it must have a relationship amongst other units, okay? Other units. So in this terms, the relationship between mass of a substance and the number of moles, okay? You can see there's a picture right over there, mass of the particles in grams, moles of particles, and those arrows there, it says the molar mass. Either you divide it or multiply it. So you can pause this video to see it, or understand it. Oh yeah, but quick reminder: please follow the units required when calculating molar mass. What I mean is that when you have a mass, okay, please turn turn them or shift them or alternate, what are the words, change the number, change the mass of the particles in grams. Do not write it in kilograms, grams. Never shift away from the SI unit, or okay, not technically an SI unit, but the required units. Okay, if it's on grams, use the gram. If it's on kilogram, change it to grams. Okay, if I'm pretty sure you know what I mean. So the molar particles, it doesn't have any units, so you're good with that. But please make sure, if you're dealing with molar mass, please change the mass to kilograms. If it's already on grams, then you don't have to change anything. It is the required units. So here is the calculation that I have found. It shows here that the number of moles of an element equals the mass of elements in grams. Remember, the required units, they need grams. They want grams, so we have to use grams. Over relative atomic mass of the element. Look at the example. Determine the number of moles or 0.16 196 kilograms of iron. As you can see, the columns, columns or brackets, I can't remember. I think it's columns. Columns AR refers to the relative atomic mass. So we can see here ferrum is 56, which means the relative atomic mass is 56. If it doesn't provide you, or in other words, if the question doesn't provide you the atomic relative mass, they most likely will provide you with a periodic table at the end of the paper of your test. They usually uh, give it. So you can search that. Remember, if you want to find the relative atomic mass, go to the periodic table. It has stated there. Uh, they have put the relative atomic mass in the periodic table. So remember, if it doesn't show up in the questions, or like what it did in columns, go to the periodic table. I'm pretty sure most teachers or lecturers will put periodic tables in at the end, at the last page of any chemistry tests. Oh, the number of moles of iron, mass of iron in grams over atomic relative mass of ions. So you can see that it's 0.196 multiplied with it with 1000 because it is in kilograms. We need the required units, so it is in grams. So we need to change that 196 kilograms to grams. So change that and divide it with 56, and you get 3.5 moles. So that's how you do it. So that's how you determine the number of moles with a method. So you might be thinking that, oh, Molar Mass is just like moles. It all has one relationship. Oh, it has two relationships. Two relationships. So the first relationship is between the number of moles and the mass in grams. But this type of relationship is between the number of moles, the mass of a substance, and the number of particles. Yes, you can find the number of particles in molar mass. You can find it. So you can pause this video to understand it. For those who never seen this type of relationship before, we can pause this and understand it. So here is the example of the second relationship, the example that I have found on the internet. You can pause this video to understand it and get to know how it works. Okay, how number of particles linked with moles, number of moles with grams, mass, moles, number of particles. This example of calculation might help you understand it. So you can pause this video. Now we shall move on to the final subtopic, 1.4.5 formula mass. Now that we have opened the door of the final subtopic, let's continue with tradition, okay? So what is the definition? Let's start with the definition. So what is the definition of a formula mass of a compound? Well, as it stated here, formula mass, also known as formula weight, is the total of the atomic weights of atoms in the empirical formula of the compound. If you don't know what an empirical formula is, basically, during high school and this first year of general chemistry, you will learn that there are two types of formula in chemistry, general chemistry. You have the empirical formula and the molecular formula. The empirical formula, the definition of empirical formula is the simplest whole number ratio of each atoms of each element that exists or present in one compound. Okay, I, yeah, that's the definition. Um, the simplest ratio of whole number of atoms in an element that exists in a compound. The molecular formula, on the other hand, is the real numbers of each atoms in each element that exists or present in a compound. So now you can know to empirical formula, the simplest ratio of whole number of atoms, like yeah, you get the point. Um, Molecular formula shows you the real value, the real number of each atoms of each element exists in a compound. Empirical formula, the simplest ratio. Okay, so it is stated here also is the total of the atomic weights of atoms in the empirical formula of the compound. So if you refer to the previous slide, it is similar to relative atomic mass, the average, but it's not really an average. It is okay. Ignore that relative atomic mass. What I'm trying to say here is the atomic weight. You total up. So let's just say that compound has three elements. Okay, three elements. So you just total up all the atomic weights of each element exists in the compound. I really hope you can understand that. So the formula weight is determined in atomic mass units, or AMU for short. The formula mass is only for ionic compounds because the molecular mass is for molecules. Although although the formula mass um, applies to molecules also, but it's more specialized to ionic compounds because, as it stated here, molecule masses is for molecule. So it doesn't make any sense to have two terms to have two terms for to referring a molecule. So the formula mass is for ionic compounds, which is basically ions, and for molecules it is molecular mass. So that's why you will see in the internet the formula mass always refers to ions and molecules, but it's more specialized to ionic compounds. So here is the example of calculation of how to determine the formula mass of magnesium chloride. You can pause this video to understand it. So what we did, so what we did back then. Is the general definition. Okay, general definition. Like I said, it also applies to ionic compounds and molecular compounds. Okay, but I did mention it is specialized for ionic compounds. So the formula mass of an ionic compound is defined as the atomic masses of the constituent I guess it's constituent atoms in an ionic compound are added to determine this a substance formula mass. Okay, this is typically applied to ionic compounds, as mentioned, which are made up of ions rather than discrete molecules. So here are the examples of ionic compounds. The first one will be sodium chloride, NaCl. Next, sodium hydroxide, NaOH. And the third is potassium chloride, KCl. You can pause this video, or I've, we all know there are lots more. There are a lot of ionic compounds out there, but I'm just going to mention three. So it is important for me and anyone who learns chemistry, is the formula mass will always equals to the molar mass. The formula mass would be AMU. The unit of formula mass is AMU equals to molar mass, that whose unit is G mole negative 1. Now, the reason why the formula mass is equal to the molar mass is because the definitions of both the mole and the atomic mass units are based on the same reference substance, carbon 12. Now that we know why formula mass is equal to molar mass, we can move on. So the atomic mass or relative atomic mass AMU also equals to molar mass, the unit as G mole negative 1. We talk about why atomic or relative atomic mass or relative atomic mass is equal to molar mass G mole in the previous slide. So you can refer to the previous slides to know why and how. Therefore, the formula mass AMU is equals to atomic mass or relative atomic mass. Why? Because formula mass equals to molar mass, and atomic mass or relative atomic mass AMU is also equals to molar mass. So if both of them are equal to molar mass, so the formula mass of the unit AMU, logically it will be equal as atomic mass or relative atomic mass, the unit AMU. So here's the equation, the calculation that I found on the internet. You can pause this video to understand. Yeah, it involves with to calculating the formula matrix. So you can pause this video and try to understand it. So now we have reached the relative formula mass, or RFM for short. Now, the definition of relative formula mass, RFM, is the total of the relative atomic masses of the atoms represented by the numbers in the formula. An easy way to explain this is a relative formula mass is kind of like the concept of relative is the average, right? The average, or in other words, you sum all of it, okay? You sum all the atoms, inner atoms. So what it means here is the relative atomic mass. See the keyword right here, relative atomic mass. So the relative formula mass is the total of the relative atomic mass of the atom represented by the numbering formula. In other words, in one particular formula, okay, you have different elements, okay, you have different elements, different atoms, okay, you total it up, you total the relative atomic mass of the atoms, okay. Yeah. Here's how you can find the relative formula mass. So the method of finding the relative formula mass is similar to finding the relative molecular mass. The difference is that the relative formula mass is specialized for ionic compounds, whereas the relative molecular mass is used for molecules. To find it, you have to sum up the relative atomic masses of all atoms. You learn this in people who took science stream will understand this, because yeah, in order for you to find the relative molecular mass and also the relative formula mass, yes, you need to sum up the entire all atomic relative of all atoms that are present in one compound. It could be an ionic compound or a molecular compound. To find the formula relative for mass or relative formula or molecular mass, you need to sum up all the relative atomic mass. Remember, in order to find it, you can go to the periodic table or they provide you in the questions. Okay, so don't worry. So here is the calculation for relative molecular mass. Okay, as it stated at the previous slide, that the formula, the how should I put this? Um, the molecular relative molecular mass and the relative formula mass is similar in terms of calculating its relative mass. Okay, so I need you to pause this video first and try to understand and look for this. Try to understand. This all I'm saying is try to understand this calculation first for relative molecular mass. Now, this is the calculation for relative formula mass. Now, I want you to pause this video to look at the questions and the answers given and try to understand and compare the relative formula mass, okay, the formula relative formula mass with the relative molecular mass. After you pause it and compare it, that you can see both the similarities of both relative masses are they both use the method of adding all relative atomic mass of atoms in an element that is present in an ionic or a molecular compound. Okay, inside of an ionic compound or inside of a molecular compound, there are atoms, right? Atoms inside of element. It has more than one metal. Okay, it has more than one elemental, right? So to find the relative mass, you have to sum up all the relative atomic mass that are present in the ionic compound. Sum it all up, and you can find the relative formula mass or relative molecular mass. That's how you find it. So we have reached the end of the video. I would like to say a million thanks to anyone who watched until the end of this video. I apologize for any language mistakes during this video, and I also apologize for the video being too long, but I have tried my best to explain the topics I am presenting in a short time. I suggest you all to consult with your lecturer for more in-depth knowledge about this topic. Um, if you are curious and want to learn more about moles and Avogadro's numbers and uh, what are the points that links with these two terms, I would say, feel free to text your lecturers, okay, for further knowledge. Anyways, that's all from me. I'm very sorry for the video being too long and multiple language mistakes. I will be I will try to be better in future videos. Okay, that's all from me. Thank you so much for sticking the end till the end of the video, and I will see you in my future videos. Muhammad Aiman out. Assalamualaikum warahmatullahi wabarakatuh. Peace be upon you.